So now we need to look at kind of a little backtrack a little bit, and we're going to look at both passive and then active circuits. Passive, consists of R, L's, and C's, but mainly, and what we're considering now is just the C and L's, because we're going to basically then turn this into active circuits where we're going to use an op amp, where we're going to have an integrator and then poles and zeros, and we're going to use that for our feedback. And, this seems like a lot of work, but again, we're teaching a course here that is going to close the loop. And we're going to be teaching to close any loop: voltage loop, current loop, continuous, discontinuous. And once you get used to the poles and zeros and how they relate to phase and gain margin and what you do to close the loop, it doesn't matter. I've closed pretty much any loops. I've closed phase lock loops. I've controlled motor speed control loops. I've controlled position loops on motors. I've controlled pretty much any power supply that's out there that I've built. I've controlled all the loops, including if I add opto isolators or magnetic feedback for isolations. It's all the same thing. You find the transfer function, you know what you want, you look at the loop, and you go step by step by step. And what you got to learn is you got to know what a zero is. You got to know what a pole is. You have to know what a right half plane zero is, so that you basically are going to be able to cancel poles and zeros to get what you want. And typically always to get what you want in a converter is a dominant single pole roll-off. And that's true a lot of times with op amps, is to have a dominant single pole roll-off. So that's how we have to start. And that's why we said, okay, we're going to really kind of go back to the basics and see what a pole is and look at how that phase changes for this pole. So the first thing we're going to look at is just a simple network. You've got the input voltage, which is just a VG. And you just have a resistor divider. So, that's as basic as you can get. You can't get any more pretty much basic than that. And you can see that the output voltage here to the input voltage is just the ratios of the impedances. And, the poles and zeros are the same thing. The only difference is with resistor circuits, there are no phasing, because the phase angle is always zero. Because you're sitting always on the real axis. So there's no phase. When you're looking at a J-axis, there is no phase. You're at always zero. Okay, so this is always a phase angle of 0 degrees. So, and that's a basic thing. Of course, pretty much, your waveform is going to be the output voltage over the input voltage is always going to be attenuated below your ground. So that's your output voltage, V out over V sub G. And you could see that's going to be down here, which is your R2 over R1, R2. And when we always talk about dBs, we always look at 20 log of the gain, which is 20 log of R2 over R1 plus R2. And that's what you're always assuming, that's what it is. And you're going to be out here, which is going to be, some minus dB, depending upon what this is. Okay? So the second really thing is, let's introduce a single pole. Let's see what that does. And then we'll, later, like I said, this is passive circuits, and later we'll do active circuits with the op amps. But it's the same concept. So here's your input. Remember, these are really Laplace. I'm not going to keep writing S's. It's going to be assumed that that's what we're talking about, the frequency domain. So if this is R1 and C1, you could see that at DC, I always walk the frequency. At DC, again, the capacitor is an open circuit. If the capacitor is an open circuit, then the output is equal to the input voltage. And therefore, the Bode plot would be output equal to the input voltage. The gain would be 1, but in a log scale, 20 log of 1 would be 0 dB. So gain of 1 would be 0 dB. And that would be, I'm plotting here the output over the input voltage. Now, what happens when the capacitive reactance is equal to the resistor value. You see, we got a dB down. We go down because now we have an impedance switch. It's this impedance over this impedance. I always call these RS and RS. So when this impedance ZO is equal to this impedance ZS, we have that point at that breakpoint. And everybody knows what that breakpoint is. That's 1 over 2 pi. If this is, of course, frequency we're plotting, and that's 1 over 2 pi R1C1. And that's derived from when X sub C1 is equal to R1, and this is 1 over 2 pi. We fix the resistor, therefore we fix this, and we call this a pole. And the reason, you'll see the reason why we call it a pole is because we go down by minus 20 dB per decade. Okay? So we could see that this pole right here is going to produce a 20 dB per decade all the way down as a function of frequency. Now, what is the circuit that's associated with this pole? Immediately when you see this single pole, you just draw the gain is 1, that's the K, and this is SC1 R1 plus 1. That's the transfer function. There it is, the output to input transfer function. That is exactly this. You could see at low frequency when S is 0, it's 1. That's here, which is, of course, 0 dB when I use 20 log both sides. And then you could see when the frequency is equal to the R1C on, then you have that breakpoint, which is 1 over 2 pi R1C1. Okay? And that pole keeps going down and down and down and down. Now, what is the phase of this? What is the phase of this? You can see that the phase here is going to be the angle of this. But you got to understand that this is an angle on the bottom. You know, S is J omega. So you could see this S is on the bottom. And if we flip it to the top, you're going to have to multiply top and bottom by what's called a complex conjugate, and you're going to get a negative J term on top. So in reality, this phase is an angle whose R1 is the real, and you're going to have this omega, this point here, as being your X sub C. It's going to be on a J axis, but it's going to be here, which is going to produce, depending upon what this is, it's a vector. And the angle we're talking about is this angle, theta. So you could see that the tangent of theta is the imaginary, this guy, over the real. And that's what it is. It's the imaginary over the real. And what we have here in the imaginary is this J omega C. So it's going to wind up being equal to the F over an FP. Okay? Well, we know that the FP is 1 over 2 pi R1 C1. And the F in general is any frequency. So when we're looking at this single breakpoint, we could see that the theta is just the arctangent, and it's of course negative. It's a negative number because it's below. If it was above here, that's positive angle. So it's minus the arctangent of F over FP. And you could see then, you could kind of plot the phase of this when F equals to FP. This is the arctangent of 1, which is 45 degrees. And since you have a minus, this angle would be a minus 45 degrees. And that would make sense. That would mean this magnitude is equal to this magnitude, and you'd have a phase angle of 45 degrees. Okay? As F continues to go up higher and higher frequencies, then you could see it starts moving this curve here, larger and larger phases, and the maximum phase would be minus 90 degrees. The minimum phase would be when f goes towards 0. That means the theta goes this way all the way down to the real angles. So you have 0 all the way up to a maximum minus 90 degrees. And that's considered what's called a pole. So now we look at, and a pole always gives you a phase lag. So now we're going to consider, well, how do we get a 0 out of a passive circuit? So we flip the capacitor and the resistor, and we have this circuit, which is the capacitor and resistor, is flipped. Now immediately, again, we want intuitive stuff as well as the mathematical stuff. And the intuitive stuff to me is, again, always walk the frequency. At very low frequency, this capacitor reactance is an open circuit because it's 1 over 2 pi f c sub 1. And that's the capacitor reactance. And at a frequency of 0, the capacitor reactance is infinity, which means that the output voltage has to go to 0 if this impedance is infinity. There's no output voltage. You can't get a voltage divider out of this, okay? Because you have infinity on the bottom, so it's going to be 0. So that means that you have to be coming up. As the frequency starts going up, then this impedance starts going down. When this impedance is equal to this impedance is when you have that break point. Again, what's that break point? That's 1 over 2 pi C1 R1. And that's equal to what? This going up is what's called a 0, the gain increasing. And what has to happen is there has to be a pole, in a sense, coming down, which is this pole coming down, which means that this is a pole. That's an FP. Okay? So therefore, what we have, and what is this magnitude? As this goes higher and higher, this goes towards a short circuit, and the output voltage is equal to the input voltage. Therefore, it's 1 or 0 dB, converting it to 20 log of 1, which is 0 dB. So writing the transfer function automatically says that the only way I'm going to get a 0 is if I get an S on the top. And that's what happens. We have an SR1C1, and we're going to have the pole is SR1C1 plus 1. Now let's look at this to see right away. To make sense, yes, you could do the math, and you could say this is 1 over SC1, and you could say, okay, the impedance is this impedance over the sum, which is R1 over R1 plus 1 over SC1. Then you multiply top and bottom by C1. I mean, this is, again, I'm not teaching algebra. I'm teaching you a method to look and find the answer immediately. C1, R1, over SC1 R1 plus 1. Happy, fine. We got the same answer. But I can see intuitively we're going to get that answer because, again, the only way that this output could be 0 at the low frequency if we have an S on the top. So we get the same answer doing it the longhand way, which is fine. Okay, so we could see that what happens is, this means the J is on the top. Initially, we have a J component up here. We have a JX, and this one gives us a minus JX on the bottom. So we're going to see that, we're going to get a phase boost because this is on the top. Its angle is going to be way up here if this is a large value. So that's going to be close to 90. So I'm going to start with a phase of 90. And then this pole is going to start dripping my phase down. So again, the very easy stuff to do is to see that I'm going to have a phase angle as starting off at 90 degrees plus and then minus arctangent of the same thing I had before. This is going to be at FP rather, and this is F over FP1. And that makes sense because you see, ultimately, what the phase is doing is starts off at 90 degrees, starts dropping off, and then starts coming back. Sorry, it comes back like that. Okay, which is going to be a phase of 0 degrees. Okay, because we start off at 90, and at higher frequency, what happens is this phase at let's say f equal to 10 fp, you're close to 90 degrees, and the phase angle goes to 0. So that's your phase. Starts off at 90 and ends off at 0. Okay, so we got the phase and gain of this system. So the next thing we want to look at is to say, okay, well, how about some kind of other signals? We have an R1, we're going to have a R2, and now we put here, all this is, similar to the first circuits that we did, but the only difference here is we DC this capacitor is an open. This capacitor is an open at DC. And we just have a resistor divider. So the only thing we do is we're starting off at a different value here of, basically, if this is the angle of 0 dB, we're going to start off at R2 over R1 plus R2. That's the DC term. And we do 20 log to get this in dB. And then this is the starting. This is walking the frequency. This is the low frequency, meaning that at low frequency, this impedance is infinity. Infinity in parallel with any resistor is that resistor. Okay?
Okay, we found a mistake in the original video clips. Here I'm going to correct this session and insert the revised video clips. Okay? Now we have a resistor R1, R2, C1 with the input voltage VG, and the output of the capacitor with the symbol V out. Now we're going to simplify this circuit into Thevenin voltage and Thevenin resistance problem. So we're going to convert this circuit into voltage Thevenin, R Thevenin, with capacitor at the output. C1, B out. And we call those two terminals B and A. Okay. Where the V Thevenin is equal to the voltage divider, R2 over R1 plus R2 times VG. Now what is the R Thevenin resistance? The R Thevenin resistance is determined by R1, R2 with input voltage shorted. When looking back, the C1 looking back at the terminal A and B, what we see is R Thevenin is R1 in parallel with R2. Okay, now we walk the frequency. At DC and low frequency, V out is equal to V Thevenin equal to R2 over R1 plus R2 times VG. At high frequency, when R Thevenin equal to impedance of C1, we have a pole, which is equal to 1 over SC1 R1 in parallel with R2. The Bode plots of the circuit, V out over VG say this is 0 dB. Below, the ratio of R2 over R1 plus R2 is less than 1, therefore it's below the 0 dB line. At low frequency or DC, this line is 20 log of R2 over R1 plus R2. The R7 resistance equal to the impedance of the C1, we have a pole. This is the pole, which is equal to 1 over SC1 R7, which is equal to 1 over SC1 R1 parallel with R2. The overall transfer function V out over Vg is equal to R2 over R1 plus R2 multiplied by the pole 1 over S C1 R1 parallel with R2 plus 1. The phase angle theta is equal to minus arctangent the frequency over the pole.
Now, let's look at how do we get some poles, some zeros, a couple of combination of a pole zero. If we look at R1 and we look at R2 and we look at C2 and we look at VO again and VO of S, it's always of S because it's a frequency domain. Again, what do we have? Looking at this, again, if this is DC, this is an open circuit. So the output has to equal to the input. So again, the gain has to be 1 or 0 dB. That's where it's going to start. Now, what happens when this frequency starts coming up to this frequency here? When the X of C2 is starting to equal to the R2. When that happens, this voltage is going to start decreasing. But before that happens, we have to make sure of the equation here, because this is going to give us what's called a pole zero. It's when this capacitive reactance looks into this circuit, you're going to have an R1 plus an R2. And what's that going to be? That's going to be what's called a pole here, FP1. And that's going to be 1 over 2 pi C2, and then this is going to be R1 plus R2. Then, when this impedance is equal to this, then it stops going down. See, that's going to, at a higher frequency, this capacitance is going to look like a short, and you're going to just have a resistor divider. So this keeps going down until this happens, where 1 over 2 pi C2 is equal to R2. And then this gain right there is just R2 over R1 plus R2. And in the log, you make the log of this. So if R1 was equal to R2, this would be a half, and that would be 20 log of a half. Okay? So you could see then, we're going to have a phase lag due to the pole and a phase lead due to the zero. So the phase is going to be, one from the pole is going to be minus the arctangent of F over FP. And the zero is going to be a plus because you're going to add the phases, and that's going to be an arctangent of F over F of 0. And this is the F of 0. So ultimately, you're going to start off at 0 degrees. You're going to come down, and then you're going to come back up to 0 degrees again. So depending upon the location of these two will depend upon how much phase dip you have. Okay, if they're a decade apart, you'll see this will come down towards 45 degrees and then come back up, be minus 45. So what is the transfer function of this circuit? Since you just write it from these parameters, you see this one and this one. So the output voltage over the input voltage is going to equal to SC2R2 plus 1 over. Okay, so then we have C2R1 plus R2 plus 1. Now, if you look at this, it makes a lot of sense because at low frequency, S is 0, that's S is 0, so we got 1 on top and 1 on the bottom, and that's where the gain is, it's 1, which is 0 dB. As this frequency occurs first, this pole comes first, you see that's where this pole comes in, it starts pulling me down, and then the 0 comes in. So at high frequency, the SC2R2 is much greater than 1, and then the SC2 parenthesis R1 plus R2 is much greater than 1, and you could see everything goes out, and it's R2 divided by R1 plus R2, and that's where this stage is. So you can see we got the high frequency end, we got the low frequency end, and then the middle goes from high to low. And that's how you can make your determination very quickly on looking at things to get the Bode plots. And these are what's called Bode plots.